Hello, my name is Matthew Abate, and today I'm going to be speaking about some of the work that myself and my collaborator Mark Moat have been conducting in the Georgia Tech Decision and Controls Lab and the Georgia Tech Facts Lab. The title of my presentation today is Verification and Runtime Assurance for Dynamical Systems with Uncertainty, and this work was advised by Dr. Sam Coogan and Eric Ferrone. The primary focus of this work is in safety for controlled dynamical systems. We'll consider systems of differential equations, as in those given by equation 1, x dot is equal to f of x, u, and w, where x is the state, u is a control input, and w is a non-deterministic disturbance input to the system. We'll assume for all time that w evolves inside an interval of possible disturbances. Okay, and we're interested in designing and verifying that feedback controllers for the system 1 maintain a safety property. So we'll say that a controller u of x is safe when it renders a given subset of the state space forward invariant. And to motivate this work a little bit, I'm showing on the bottom of the slide some figures that describe the safety paradigm that we're moving towards, and specifically these figures describe runtime assurance. So runtime assurance mechanism acts as a filter that stands in between the controller and the plant. All right, and so given a desired control policy that is perhaps not safe, this runtime assurance mechanism will apply the desired control input to the system when it is safe to do so, and when it is not safe to do so, the desired control input will be modified so that system safety is maintained online. And looking at the figures, we're given a system, as given by equation 1, and a safe set of states, as shown in green on the lower right. A desired controller is provided, however this controller drives the system outside of the safe set, and this is shown in red on the lower right. Okay, so just one focus of this work is in designing this runtime assurance mechanism that allows you to achieve the blue trajectory, which is formed online via an analysis of the desired control actions, the current system state, and the bounds on the disturbance set. So now that we've motivated the work a little bit, I'm going to discuss the two main problems that we go after in this work. So the first is just the controller verification problem. So we're given a desired feedback controller UD and a safe set of states, and the goal of the controller verification problem is to show that this safe set of states is robustly forward invariant for the closed loop dynamics of the system under the desired control action. All right, and we'll assume for the time being that the safe set of states is a hyperrectangle or interval in the state space. Okay, our second problem, as alluded to on the previous slide, is the runtime assurance problem. Again, we're given a desired feedback controller UD, but the goal of the problem is to design a controller UA, which maintains this forward invariance of the safe set, but also so that UA evaluates to UD whenever possible or whenever it is safe to do so. So we solve these two problems in this work, and we actually consider two extensions of both problems as well. So we consider controller verification and runtime assurance in the presence of state uncertainty. The idea here is that your runtime assurance mechanism UA might not have access to the current system state, only some, say, a set where your state is known to live. And we also consider a second extension, which is controller verification and runtime assurance for polytope safe sets S. So initially we're just going to go through some of the results of this work in terms of hyperrectangular or interval safe sets, and then later we'll move on to the more general class of polytope safe sets. The main theoretical tool that we're going to use in this work to solve the runtime assurance and controller verification problem is mixed monotone systems theory. So again, we're considering systems x dot is equal to f of x, u, and w, and we'll say that this system is mixed monotone when there exists a related decomposition function d, which separates the system dynamics into increasing and decreasing components. Equivalently, d is formed to satisfy the 5 points on this slide, and I won't get too deep into what these individual conditions mean, but just for a high-level overview, the first condition listed on this slide, this relates your decomposition function to your initial dynamics. In conditions 2 through 5, these are derivative conditions on your decomposition function, and they're used to form a related embedding system with monotone dynamics. So we'll see this more on the following slide. Okay, so when your system x dot is equal to f of x, u, and w is mixed monotone with the decomposition function d, you can take this decomposition function and you can use it to construct this deterministic embedding system given by equation 3. And this embedding system has two useful properties. So the first is that it's a deterministic system. It no longer is affected by a disturbance input. And the second useful property is that it is a monotone control system with respect to a specific order on this higher state space x cross x. This embedding system has been applied for several useful results for efficiently computing reachable sets for your initial dynamics, and also for efficiently computing robustly forward invariant sets for your initial dynamics. We won't discuss the related results that much in this presentation, but I'm including a reference here to a recent tutorial paper on mixed monotone systems, which you should all check out if you get a chance. It's a really good read. The second theoretical tool that we'll be using in this presentation is the theory of control barrier functions. Okay, so control barrier functions in the setting with disturbances are mainly used for systems that are control affine, so systems of the form given by equation 4. A function h is called a robust control barrier function for the system 4 when there exists a class k function alpha, so that the condition 5 holds for all w in the set of possible disturbances. When you have a robust control barrier function for your system, you can use it to construct a runtime assurance mechanism for your system that enforces safety over the super zero level set of h. However, generally constructing runtime assurance mechanisms in this way leads to a runtime assurance mechanism constructed as a quadratic program with infinitely many linear constraints, and for this reason it can be computationally intensive to actually apply this mechanism in practice. So what we're going to do in this work is we're going to take some of the mixed monotone systems theory that allows you to construct a deterministic embedding system from your initial dynamics, and we're going to mix that with control barrier function theory in order to arrive at a runtime assurance mechanism that contains a finite number of linear constraints in the program. So in this way, we are able to attain a runtime assurance mechanism that is practically implementable for systems with disturbances. So on the next few slides, I'll be discussing our results related to controller verification via the mixed monotonicity property. So our first result reads as follows. Choose a desired controller UD if there exists a class K function alpha, so that the constraint 6 holds for all x in your safe set. Then your safe set S is robustly forward invariant for the closed loop dynamics under D, and in this way you have verified that your desired controller is a safe controller. In this condition, given by equation 6, it bears a lot of resemblance to the robust control barrier function conditions provided on the previous slides. The idea is that you take your initial system dynamics. If it's mixed monotone, you arrive at a decomposition function for that system, and this allows you to construct the related embedding system. And really, you can think of the constraint 6 as though it is a control barrier function type condition, but applied to this deterministic embedding system. And because of the fact that the embedding system is deterministic, there aren't disturbances that pop up in the constraint, and this allows you to verify desired control inputs are safe with relative computational efficiency. And now I'll be presenting an example of the aforementioned controller verification result. We're going to consider a system given by equation 7. So there are 6 states, a 2-dimensional control input, and 2 disturbance inputs. And this system comes from the Cholesky-Wiltshire-Hill equations that describe spacecrafts in orbit. So on the following slides, what we're going to do is we're going to define a safety constraint for the system. We're going to propose a desired controller for the system, and then we'll verify the fact that this desired controller satisfies the safety constraint. Okay, so safety for our spacecraft system is going to be defined in terms of distance to what is called a periodic natural motion trajectory. Okay, so consider for a moment the definition of x given by equation 8. The system is said to be in a periodic natural motion trajectory when x is equal to 0, and in this case, your state, y, which lives in 6 dimensions, it will make closed periodic orbits around the origin of the initial state space. Okay, and the non-deterministic nature of the initial system actually prevents you from maintaining a single natural motion trajectory while in orbit for all time. However, you can use this definition of x in equation 8 to come up with a relative metric of safety. That is that it is beneficial for a control systems designer to try to minimize the value of x at all times when possible, so that if you ever experience a runtime error, you know that your system will not drift significantly off its initial course. So now that safety is defined in terms of the parameters x, we need a dynamical system representation of the dynamics of x. So these are given by equation 9. And on the following slide, we're going to propose a desired controller for this new system, and then verify the fact that it enforces the robust forward invariance of an interval about the origin in the x space. Okay, so this desired controller is given by equation 10. And now, applying the aforementioned results with an embedding function for the closed loop dynamics of the x system under UD, we are able to arrive at this relation given by equation 11 that describes safety for the system. So what the equation 11 is telling us is that, say you construct some safe set in the state space of x, right? This safe set is given by s underbar, s overbar. As long as your disturbance set is contained inside your safe set, because remember now they're both two-dimensional, as long as this is true, the S set will be robustly forward invariant for your X dynamics when the desired controller UD is applied to the system. And thus, it follows that UD is safe anytime your disturbance set lives inside of your safe set. Okay, so this wraps up our example. Now that we've presented our main controller verification result and presented an example describing how this result is implemented in practice, we'll discuss some extensions of the result. And the first extension comes when your controller is operating based on uncertain state measurements. So the way that we formalize this is we define something called an uncertain observer, and we're going to assume that this uncertain observer at all times t provides a hyperrectangle in your state space where the system is known to live. We don't make any assumptions on the size of this observed set. It could be the entire state space. Only that your current system state is known to live inside this observation. Okay, and this allows us to redefine the controller verification problem. So now we're given a feedback controller which operates based on the uncertain state measurements, and we are asked to show that this candidate controller renders a safe set forward invariant when it is applied to the system. And the solution to this problem is given by the theorem on the bottom of this slide. So now we have a new embedding system barrier constraint that's given by equation 12. And when this constraint is satisfied, you know that your desired controller, which operates based on these uncertain state measurements, verifies the robust forward invariance of some region in your state space. And this is our first extension. Our second extension involves convex polytope safe sets as opposed to the interval safe sets considered on the previous slides. So we're now going to consider a set S, which is a polytope, and it's defined as the intersection of parallelotopes in your state space. So a higher order parallelogram. when your safe set is defined in this way, you can construct a new constraint given by equation 13. So when your embedding system satisfies the equation given equation 13 for some class K function alpha, then you know that this polytope safe set S is robustly forward invariant under the closed loop dynamics of your desired controller. All right, so at this point, we've discussed tools for verifying controllers render regions robustly forward invariant. And in the case of no state uncertainty, and we've also considered now polytope safe sets. So I'll next be discussing our results related to runtime assurance for mixed monotone systems. Okay, and we're going to begin with an assumption on our embedding function. So we'll assume for the time being that the embedding function for your system is affine in control, so that equation 14 is satisfied for some functions E1 and E2. Okay, so this is reminiscent of the fact that control barrier functions generally operate on a control-affine system. Next, we're going to define a notion which we call embedded invariance. So we'll say that the set S is embedded invariant for your initial dynamics when there exists a class K function alpha so that the constraint 15 is satisfied. Okay, and we're going to use this notion of embedded invariance to construct runtime assurance mechanisms that enforce the set invariance of S regardless of the disturbance experienced online. So this runtime assurance mechanism is constructed using equations 16 and 17. When your safe set S is embedded invariant for your initial dynamics, an assured controller is given by this ECB-FQP 1617. It's a quadratic program with 2n linear constraints, so it's a finite number and linear with the dimension of your state space. And this assured controller will render S robustly forward invariant regardless of the desired input policy chosen. So when provided a desired controller that is perhaps unsafe, you can use this ECB-FQP to filter that desired control action to arrive at an assured control action that guarantees system safety. And before we demonstrate this result through examples, I'll touch on our extensions here as well. So we also extend the aforementioned runtime assurance results to the setting of state uncertainty, and also as well in our work to the setting of polytope safe sets, as we'll see later. But when you have state uncertainty, you can construct an assured controller using the quadratic program given by equations 18 and 19 on this slide. So now I'm going to provide an example of the aforementioned runtime assurance results. So we'll consider this non-deterministic polynomial system given by equation 20. There are two states, two control inputs, and a scalar disturbance that affects the system, but this scalar disturbance affects the system in both state dimensions. And we'll assume that for all time W is greater than a negative 1/2 but less than 1/2. Okay, and this system 20 is mixed monotone with respect to the decomposition function given by equation 21, and you can use this decomposition function to then construct the embedding system relative to the initial system. So now on to defining a safety specification for the system. We're going to choose arbitrarily an octagon safe set, which is just described as the intersection of two parallelograms in the system state space. Okay, control actions for the system are going to be made using an uncertain observer, and this uncertain observer is going to at all times provide a circular subset of the state space where the state is known to live. So this problem setting is shown on the bottom of the slide in the figure. Our safe set is shown in green, which is the intersection of two parallelograms in the state space. Our system state is shown in blue, but we don't have access to the system state. Only an observation where the system state is known to live. So this is shown in red, and for some figure clarity, the blue dot is not the center of the red observed set. As we'll see later, the red set will move around the blue region. And the goal of this work is to design a runtime assurance mechanism that operates based solely on the uncertain state measurements, but is able to ensure the fact that the blue trajectory stays inside the safe set for all time. And this assured controller, it's straightforwardly provided by the ECBF quadratic program discussed previously. So we're just going to implement it. We're going to take the open loop control policy given by equation 23. The previous results are cast in terms of feedback controllers. However, open loop control policies are accommodated in the results in a similar way. And when we apply this assured controller to the system, we see that the desired controller will drive the system outside of the safe set if not preempted by some filter. And in this filter that we construct using the ECBF quadratic program, it does just that. It maintains system safety and forms a control policy which is similar to the desired control policy, but which renders the safe set forward invariant. One interesting thing to note here is that the results of our work do not guarantee the fact that the observed set, the uncertain observer set, lives inside your safe set for all time. You can see in this figure that actually the state observation has moved just slightly outside of the safe set. So you can think of the fact that your observer is telling you here, you might be unsafe. Your state might not be in the safe set. However, certain properties of the ECBF controller allow for this with the additional guarantee that wherever your state lives inside this observed set, it must be inside the safe set as well. And we see that here in the figure. So while the observation set is just peaking slightly outside of the safe set, the assured controller knows this, but it knows the fact as well that your actual system state must be safe, and therefore allows the observation to move outside. And this is interesting as well. The assured controller is able to infer the fact that the system trajectory is safe, even though the observation is telling it that it might not be. So with that, I'm going to wrap up the presentation. I'd like to thank you all for listening. In this work, we show how controlled invariant sets for mixed monotone systems are identified via a CBF type condition for the related embedding system relative to the initial mixed monotone dynamics. And we use this observation to construct two techniques, one for verifying feedback controllers against safety constraints, and one for designing runtime assurance mechanisms or assured controllers that enforce the set invariance and controller safety online. Great. I'd like to thank you for listening. My name is Matthew Abate, and I've included my contact information on the bottom of this slide.